Hello everybody, welcome. Welcome at the first session of the third season already of these Getting Technical Live events. In previous sessions, we have been talking quite a lot about machining processes, and we define the machining process as something where there are rather high pressures appearing on cutting tools, and there are high temperatures, and lots of heat is generated. And from a tribological perspective, there is some severe attacks on cutting edges. And it's good to discuss about those things and to know about these things, but it's also good to take it on a more practical level and start talking about, okay, we know, but the tools we use, the cutting tools we use, which properties do they have to have? Which features do they have to be capable to cope with all those phenomena? And today's session, noticeable, it's the first part of a two-part event, is about cutting materials, advanced cutting materials. And if we talk about advanced cutting materials, the little word advanced has several meanings. Advanced can mean latest, developed in time. Advanced can mean sophisticated. I leave it a little bit in the middle here, what exactly we mean with advanced. Let me say it's in a sense of modern cutting materials we talk about here. And we are going to approach cutting materials in such a way that we say, okay, we know what's going to happen, we know what is happening during machining processes, but how about the properties of cutting materials? How about matching the correct properties of cutting materials in certain machining processes so that the process happens in a reliable, productive manner? And that is what we are going to do today and next time, because as I say, it's a two-parting. And I'm not alone here. I'm here together with Alesia and Margarita. They are going to take care of this event behind the scenes, as I always say. Very important, because today, for the first time, we are going to do something new. I have two colleagues of mine, Francesc and Perola, and both of them, they are specialists when it comes to advanced cutting materials. So when there are questions, I'm going to have the help here of two friends, two colleagues of mine, to make sure that we take care of your questions in the best possible way. So today it's and we are going to do that live. That's why the role of Alesia and Margarita today is so important. They will have to make it happen, that things goes in a correct way. Now, trends in machining production, because if we talk about cutting tools, we cannot see the developments in cutting tools loose from what's going on in machining production, because it's the two go together. We develop new cutting materials because there are certain trends happening in machining. And due to that certain trends appear, we need to develop other cutting materials. It's working in both directions. And if I look to very, very briefly here, and just to make sure that I don't lose too much time on details, what you are going to see is that I blacken the screen now and then to make it for myself an obligation to stick to the major points here. This presentation, of course, as always, is available for you as reference. If you want to receive the presentation afterwards, just send me an email with your information and you have in return the presentation, where the text is not blackened, so you see all the details here. But if we look machining production, what is important in machining production today more than ever is cost efficiency, it's flexibility, it's variability, it's quality of finished workpieces, it's productivity, the traditional stuff, but it's also about environment. Doing machining in such a way that we have some respect for resources, material resources, for energy, that we don't put too high loads on the environment. That is rather new when we talk about machining. And in such a way, we more and more talk about sustainable machining also as something which is important. Doing machining in such a way that we fulfill the needs of today. Of course, we need workpieces today, but we should not jeopardize the future by doing that. And that means that those big trends we see in machining production, if I look a little bit narrower now to the technology of machining, it means that people are looking for quite a lot of things, but a big thing is increased cutting conditions. That is what we talk about in terms of productivity, cost efficiency, and so on. It's always that quest for faster, and also new machining strategies. And perhaps the most, and now I'll shock perhaps some people, the most important machining strategy, I always say, is additive machining. And people say, "Ooh, additive machining, that's not machining, that's something else." It's depending on how you define it, but it's very clearly that people are very much into looking into new methods, new approaches to produce workpieces. Advanced cutting materials like PCBN materials, PCD materials, ceramics has to be seen in that context. Of course, productivity and cost efficiency are important, and that is that quest for higher cutting conditions. But it's also the environmental things, the green machining that plays a very important role in this development. Because with these cutting materials, as we will see later on in detail, it is possible to do certain machining processes in a more environmental friendly manner, in a more energy efficient manner, in a more green approach. And that is one thing. On the other hand, there is developments in workpiece materials. More and more we see workpiece materials with properties which were years ago not possible, functional properties, then I mean. And we see better and better workpiece materials. But what most of those better workpiece materials have in common is that their machinability is lower than before. It's more difficult to machine those workpiece materials in a productive, cost-efficient, and sustainable manner. And this is a very clear thing, that certain workpiece materials appearing on the scene, appearing in workshops, and advanced cutting materials, they kind of go together. We see more and more alloyed ductile irons being used. We see compacted graphite iron. We see powder materials. We see high chromium content materials. And those things, machining with the traditional tooling is problematic. With PCBN, on the other hand, it's easier. I'm not going to say it's easy, but it's easier to achieve productivity targets, cost efficiency targets, and so on. Another thing we see is titanium, composites, various types of sandwich materials, silicon content aluminiums, and so on. Also a very clear development in those materials we see. And those materials, when they have to be machined, that's when PCD, diamond, appears in the picture. And we also see that more and more of the so-called superalloys have increased nickel contents. We see powder metals with nickel content. We see materials like waspalloy in the aerospace industry appearing more and more. And if you look to that type of materials, to do their productive, cost-efficient, sustainable machining, ceramic tooling peeps around the corner. So we see that, and in the meantime, I have been kind of defining what we call advanced cutting materials. It's PCBN materials, cubical boron nitride, it's PCD, it's diamonds, and it's ceramics. Those three kind of we call the advanced cutting materials. And they, on the one hand, follow trends we see in machining in general. On the other hand, they follow material trends. And what I try to say here is, very briefly, very shortly, is that we see more and more materials appear in a workshop that we didn't see before. A lot of those materials have in common that they are difficult to machine, and people in workshops, they dream, they hope to machine those materials like they did steel in the past. And that is where the advanced cutting materials then come on the table, because they mean a big step forward in that way of thinking. Now, a few words on cutting tool selection, because cutting tool selection, part of the overall picture is, of course, cutting material selection. Cutting tool selection, you know, we have been talking at a previous session about this. Cutting tool selection for me is a management task in a company. At least the big picture. Because tools needs to be, or the selected tools needs to be in line with the company KPIs and the overall company KPIs. And company KPIs is cost efficiency, time efficiency, quality of finished products, total turnover, total output, and sustainability. That is the 5 classic traditional manufacturing KPIs in a manufacturing company. And cutting tools should be in line with that. And there are tough decisions needed there, because it's not always easy to prioritize things. Because to in these 5 KPIs, one can go for number 1, productivity, or economy, or versatility, or quality, and depending on what is decided most important, tool selection needs to be in line with that. Productivity, if that is the company KPI, that is priority 1. Well, the tools you select should show high performance. If versatility is important, you need tools with a broad application domain. If economy is important, you need tools with the lowest possible cost per cutting edge per tool life. And if quality is an important company KPI, then you need sustainable and precise cutting edges. Filling in the details later on, that's a technical activity. Once you have the big decision, I need high performance tooling, or I need versatile tooling, make it happen, that is about technical details, which geometries, which carbide grades, and so on and so forth. And today, noticeable, we are going to talk one of those technical things called cutting materials. When we talk about cutting materials, we have to be aware, of course, that cutting materials, it's not an island. In the technological description of a cutting tool, a cutting material is kind of the linking between workpiece materials and cutting speeds. These 3 always go together. So if we talk about cutting materials, we have to talk about workpiece materials. And if we talk about a combination workpiece material, cutting material, there is a cutting condition we need to discuss also. That's the cutting speed. Now, modern cutting materials, let me sketch you first a broad picture, a general picture. If we look to what we talk about, modern, and I don't know if I should call tool steel a modern cutting material, but anyway, this represents roughly the last century. We see tool steel, we see high-speed tool steel, the Taylor steel, we see cemented carbides, we see ceramics, we see CBN PCDs, we see cermets. And if you look here to when more or less these things were introduced, it's the youngest one, cermets, it's already 40, 50 years we use that. So be careful with these things, because this means also that all these families, CBN, I remember beginning of the 80s, CBN was the cutting material. There was only one called CBN. That's it. Today, CBN is a name of a family. And in CBN, we have lots of different types of CBN, also called CBN grades, like we have carbide grades. So all of these words, remember, ceramics is a family of cutting materials. CBN is a family of cutting materials. PCD is a family of cutting materials. The only thing they have in common is the core material, the basic material from which they are produced. And if we look to modern cutting materials, basically we can say that we have 3 big families. We have what the family of the cemented carbides, uncoated, coated. Cermets belong to that family because a cermet is a cemented carbide with a specific composition. A second big family is the ceramics. Also here we have different types of ceramics, like we have different types of carbides. We have oxide ceramics, mixed ceramic, whisker reinforced, and so on. We have the CBNs, and we have diamonds. CBN and diamond, I don't know. Very often we put it in one family. I don't know if it's correct or not, but that's tradition of doing it. These are the big family names, and very often talking about those families, what people show you is a diagram looking like this, where we rank cutting materials based on their basic physical properties, being the horizontal line, toughness, or transverse rupture strength, and the vertical line represents hardness, hot hardness, wear resistance. Very classic way of showing. And then we classify and we say certain cutting materials are very tough but not so hard. Traditional physical thinking, and others are very hard but not so tough, and so on. A diagram like this looks nice, but personally, the scientific value of it is very questionable. But anyway, I show it you here, because here it allows me to define a little bit better already what basically people talk about when they talk about advanced cutting materials. You see the cutting materials to the left, upwards towards higher hardness, higher hot hardness. That group of materials, the ceramics, the CBNs, the PCDs, that is what we refer to as advanced cutting materials. It's a way of defining. We talk about the carbides, the more traditional cutting materials, and we have the advanced cutting materials. Now, if you look to a cutting edge today, it is during machining submitted to quite a lot of physical phenomena, and it needs resistance against quite a lot of things. It needs resistance against pressure, fatigue, fracture, bending, resistance to heat and high temperatures, to abrasion and adhesion, to chemical reactions, and so on. And that means that metallurgists, they try to combine certain materials to find certain possibilities to take care of all of this. What we should not forget, not the subject of today, we have been spending a couple of months ago a session on it, that is that the cutting geometry, of course, also plays a role in this. The cutting properties, the cutting possibilities of a cutting edge, it's not only the cutting material, but it's also the geometry. It's the two together. And we will see next time when we talk about CBN and so on. You know, you can have the best CBN grade in the world, but if you combine it with the wrong geometry, you'll destroy it in seconds. I think, I don't know, perhaps Perola or Francesc would correct me when I say this, but I think exploiting fully the properties of CBN or PCBN demands also very serious thinking about the geometry you use on the cutting edge. But anyway, that's another subject. I just want to bring it under your attention. Normally, when we talk about cutting materials, I already said the traditional way, the physical way, hardness, toughness. Now, from a cutting perspective, from a machining perspective, a cutting edge has to show wear resistance. It has to show shipping resistance, fracture resistance, thermal resistance, and iron resistance. Iron resistance is another word for chemical inertia. It should not react in chemical ways with the workpiece material. And what you see here is another type of diagram where I rank the five families we talk about, the ceramics, PCB, PCD, and carbides, based on how they behave when it comes to these five properties. And going in depth about this, that is what we are going to do when we discuss more in detail the possibilities of these materials. And of course, what I already said before is whatever cutting material you select or you decide that could be most probably best choice in your application, a selection of a cutting material is not an island. It does not stand alone. It is related, it is connected to workpiece material properties, and the linking between workpiece and cutting material is mainly the cutting speed. To some extent, in some applications, also the feed plays a role. And in the toolbox of every machinist should be this awareness now that whatever cutting material you select, you should know the main properties or the big advantages. Is this cutting material mainly wear resistant, or is it fracture resistant, or whatever? And then you should exploit that in relation to the workpiece material and the demands the workpiece material will put on the cutting edge, and exploiting the advantage of a cutting material you do by an intelligent selection of cutting conditions. If you see here two examples, imagine you have been selecting a cutting material due to its toughness. If you want to use that toughness now, you use that by using higher feeds. You use it by selecting sharper cutting edges. You must be careful to keep your cutting temperatures low, so you should keep your cutting speeds low. Otherwise, you would destroy the toughness, which was your basic choice. So cutting material selection relate to workpiece material selection, and the intelligent or the expert machinist know how to connect the two, knows how to exploit certain properties. Now, cemented carbide is today considered the most versatile material. It's kind of the standard, although I don't like to use the word standard because it means that the others are not standard. But it's the base, it's the core, it's normal, it's classic. And if we talk about modern cemented carbides, we talk about carbide substrates, we talk about different layers, we talk about coatings, we talk about attribute coatings, things which are added for extra reasons on cutting edges. And based on how we combine things, we can divide cemented carbide in quite a lot of subfamilies. And those subfamilies then, that's what machining people have to find their way in. And today there are quite a lot of carbide. I think I'm not exaggerating when I say there are thousands of different carbide grades. Be careful when we talk about carbide grades. People very often start talking about ISO, the ISO system to classify carbide materials, and they even try to use this ISO classification system to classify advanced cutting materials, which is a very dangerous exercise to do. But anyway, remember that this ISO system classifies applications, not cutting materials. P10, as an example, is an application. It's not a cutting material. You have to be very much aware of that, because otherwise you are due for some serious accidents, perhaps, during machining. Now, the big advantage of cemented carbide being so many different types available is also the biggest shortcoming. There are so many that's becoming very difficult to make a selection. And that's why I always say, that's one of the reasons I say, before going into details on management level in every machining company, should be decided what is the core thing we expect from our cutting tools. Productivity, is it high performance? Cost efficiency, is it low cost per cutting edge per tool life? Is it quality? Is it sustainable cutting edges? That should guide the machinist expert in making the detailed selection of a carbide grade. Now, in carbide technology, what people always are interested in what is latest development. I think the latest development in carbide, perhaps the most important one of the last 10-20 years, is that the pure nature of a carbide insert, a cemented carbide insert, And some older people perhaps remember that in the past we talked about throwaway inserts, meaning once they are used, once the tool life is reached, they are thrown away. That nature of this, that feature of a tool is changed, and today cemented carbide inserts are in a circular system. Cemented carbide, once used up, is recycled, and the materials in it is used again to produce new cemented carbide inserts. So we moved away from the throwaway culture in cemented carbide inserts to a circular system. Coatings. I'm not going to spend too much time because this is a subject on its own, coating technology. Today we are so far in doing things with thin layers. It's incredible. But on the other hand, it has a drawback, and the drawback is that the wear resistance of these coatings is so high, so good, that there is nearly no wear appearing on cutting edges. It looks like it can cut forever, and then suddenly it breaks. And that is the drawback, that we have to use, we have to have other systems for evaluating if a cutting edge is still capable of cutting or not. That's why we developed systems like what we call GTDA, for instance, which will help us in a preventative manner, in a predictive manner, to predict how a cutting edge is going to behave from a wear perspective. Cermets, as I already said, cermets is basically carbide, but carbide where the core material is tungsten carbide. When cermets, the basic material is titanium carbide. But for the rest, I put it under the same family as cemented carbides, cermet materials. There are also what we call ESP materials, extra small particle, very small grain sizes, which is also cemented carbide. Here we talk about the grain. This is the typical materials we use for solid carbide tools, solid carbide milling cutters, solid carbide drills, where we need very high toughness and where we need sustainable cutting edges. Sharp cutting edges, and stay sharp for a longer period, and the feature we use for that is ESP cutting materials. As I already said, to selecting these materials, we have the ISO approach, but when you use it carefully. Be very, very much aware of that ISO classifies applications, classifies workpiece materials, and how they will behave when you do machining. Your selection of a cutting material needs to be in line with the properties of a workpiece material, but the intelligent machinist must link the two together. And that is by selecting in a smart way the correct cutting conditions, mainly cutting speeds, to some extent feeds. Another way of showing this ISO system is this diagram. This is more, I would say this is kind of more a global tool, a global approach, where if you know which type of workpiece material you have and which type of loads the workpiece material will put on the cutting edge, that you can classify families of cutting materials in such a way that you find what it's kind of a rough approach for selecting cement cutting materials. The same approach exists for coatings, because as I said, coatings, there are so many coatings today that it's good that we have a lot of choice between different coatings, but from another perspective, when we talk about having to select a certain coating, that makes life not so easy that there are so many coatings. I mean, cemented carbide, considered today as the most versatile cutting material. There are thousands of cemented carbide grades, which is good, which is also problematic for those who have to make a selection. Advanced cutting materials. What do we talk about when we use the word advanced cutting materials? We talk about PCBN materials, polycrystalline cubical boron nitride. This material in detail we are going to talk about in the second session next month. Another group is the polycrystalline diamond, industrial diamond, PCD. We are in a couple of minutes going to talk a bit about PCD cutting materials, and ceramics. Ceramics also we'll deal with at the next session. In which machining technology do we use these materials, or where are they at their best? I would say hard and dry machining is a very typical application for these materials. Ultra precision machining is very typical, and non-ferro machining is very typical. What you see here is a combination of applications which before, in an economical, defendable manner, was not really possible with cemented carbide. The other thing that plays a role here is the environmental thing, as I already said. Look at hard and dry machining, no cooling used during machining. Which materials? As I said, these are not just single materials anymore, these are families of cutting materials, different grades exist. And these can be used in all workpiece materials in a bit of selective manner, like with carbide. Why do we use these advanced cutting materials? To solve a technical impossibility, a material we could not machine with cemented carbide, as an example. For technical improvements, for instance, PCD and aluminium machining with extremely high cutting conditions for productivity, or to improve production economics, to be more reliable, cost efficient, productive, everything together. Now, during these presentations, we are not going to talk about materials, cutting materials with nanolayer coatings, because that's quite a subject on its own. We are not going to talk about CVD diamond, because it's I would say it's still under investigation, really, to fully understand the possibilities of that, like it is with nanolayer coatings. And we are also not going to talk about wurtzite boron nitride, which again is a very specific material. I would say it's still in a laboratory environment and not fully available for normal production. Now, if we, like I did in the beginning, a bit try to position these things from a physical perspective, their hardness, their fracture toughness, and their thermal conductivity. You see in the bottom traditional carbide, and then you see the different materials which are in the family of advanced cutting materials, PCB and PCD, ceramics, and ceramics is like carbide. And we see in hardness, with the exception of PCD and CBN, that they are all in the same range, more or less. Fracture toughness, we see that they are all more fragile than traditional carbide. It's something we have to be aware of. And thermal conductivity, here we see a mixed picture. When we talk about ceramics and ceramics, thermal conductivity is lower than carbide, while when we talk about CBN and PCD, in average, thermal conductivity is higher. Now, for those who do not fully appreciate thermal conductivity, I can translate thermal conductivity here in a sense of capable of handling high heat generation during machining, capable of handling high cutting speeds. I make a very general statement now. With hardness, we need to be careful, because we talk about hardness and we talk about hot hardness. Hardness is, I could say, it's the hardness a material has at room temperature. Hot hardness is the hardness which is remaining at certain temperatures. And what we see then, and you see here again the different families of cutting materials, when you have hardnesses at room temperature, the moment you start to increase, and remember traditional cutting today, we talk about temperatures which are around 1000 degrees Celsius, we see that whatever cutting material loses its hardness when the temperature goes up. It's a physical constant. But anyway, if you take, for instance, CBN and you compare it with carbide, what we see is that the hardness of CBN compared to carbide at high temperatures is that CBN keeps a hardness which is the hardness of carbide at room temperature. And in that understanding, we find quite some answers to questions people ask. You see the black line, a very specific line for diamond. I'm going to come back to that in a couple of minutes. Diamond is extremely hard, but I talk about industrial diamond here, is extremely hard, but at certain temperatures, somewhere around 600-700 degrees Celsius, it loses its hardness completely. And that's something we have to be aware of when we use it as a cutting material. And now to end the session of today, some words, some more in detail on PCD. Polycrystalline diamond we use today as a cutting material. If we try to classify diamond as cutting materials, we have natural diamond, which is in some applications used as a cutting material. Next to that, you have the HPHT synthesized diamond, the traditional, the classic industrial diamond, high pressure, high temperature synthesization. And there we find monocrystalline and polycrystalline diamonds. I'm going to come back on it. And then you have the CVD synthesized diamond. But as I said, that is not truly part of today's presentation, as it is a chapter on its own, that group. So I'm going to focus mainly on the part in the middle here, the classic industrial diamond. Now, diamond is, let me start with the natural diamond, also called the single crystalline diamond. It's the hardest material in the world, although Wurtzite is challenging that, but leave that in the middle if that is correct or not. It's used as a cutting material. People do not really realize that this is used as cutting material. Not especially in machining, metal machining, but in other applications. Yeah, cutting glass, for instance, we use SCD materials as an example. And it shows a tendency to be used more and more. One big disadvantage of single crystalline diamond is that the strength of it is depending on the direction you look to the structure. A skill, seeing that, a skill that, for instance, a diamond cutter to make jewels possesses to a high extent, because you can cut diamond if you know in which direction to make your cutting movement. For practical reasons, this thing is a bit tricky. We prefer much more, when we talk about machining in metals or metal materials, the PCD form, the polycrystalline diamond. It's a composite material. It's partly diamond grains, it's partly cemented carbide, cobalt also, and it's kind of a cemented structure. And as I describe it here, you have diamond grains, you can have big grains, small grains. It's connected with cobalt. You can use a lot of cobalt, you can use lesser cobalt, and you hear me coming slowly that in diamond PCD in the past we had only one. Today we already have a whole family of diamonds or PCD grades we can use. The perhaps biggest advantage compared to SCD, single crystalline diamond, is that the properties of PCD are in all directions the same. It's very often told that it's expensive. Here you have to make a distinction between the purchase unit price, and that is rather high. But if you use the tool in an effective manner, as it is supposed to use, the production cost of it, the cost you have to carry in your production to pay for your diamond tooling per workpiece or per production hour or per whatever you want to calculate, is extremely low when you use it in the correct applications. Mono and B model grades. Mono is I have one type of grains in the structure. B model is that I combine different grain sizes to create a stronger structure. That creates two subfamilies. Talking about grain sizes, you have to see like this, that how should I say this? From a machining perspective, from a cutting perspective, big grains are best, because they give you higher abrasion resistance, they give you higher thermal conductivity, all good things when it comes to the properties a cutting material must have when you do machining. However, if you go for sustainable cutting edges, with other words, cutting edges with a high edge quality, sharpness, and stability, that it keeps its sharpness, those things we refer to as sustainable cutting edges, then it's better to go for fine grain sizes, small grain sizes. So it's a bit, and again, now I'm going to make a statement that some people perhaps find shocking, but one could say diamond can be used for roughing operations where we need the abrasion resistance, where we need the high thermal conductivity, and there are CBN grades which we can, PCD grades, sorry, which we can use for more finishing type of applications. Now, most of the time when we talk about CBN, PCD, people start talking about the properties. Here I blacken the screen again. As I said, if you want to have this presentation, please leave me a message, send me an email, and I make sure that you have a copy of this presentation. There you'll see what is blackened out here. But what is important for me is that depending on the different properties of these materials, these PCD materials, you have a tool with sharp cutting edges that can be used with a very long tool life. So tool exchange and index times are close to zero. With one tool, you can continue to cut and cut and cut, which is very favorable, for instance, for your OEE. They show a low tendency for build-up edges. So you can do high precision cutting during the whole tool life of the tool, which is good for high quality machining, hard machining, high precision machining. You have to be careful. I don't say it's impossible, but you have to be careful with intermittent machining, where you have at certain moments perhaps rather big impact loads, and then if you manage to limit that, there should be further no problem. And one property is very important, that is that you have to be very careful with PCD when you do machining of a material in which there is a big amount of iron. Because what is happening is two things. As I said, PCD is a material where you have diamond grains and they are linked together, they are cemented together with cobalt. Now, if the temperature to which the cutting edge is submitted is too high, the cobalt will act as a catalyst in a reverse system and will make that diamond, which is carbon, that the carbon structures change and connects with iron in steel, for instance. And that means that if you put PCN in contact with a material in which there is iron, and the temperature for a longer period, because this diagram shows you the horizontal line is cutting time in minutes, the vertical line is the temperature to which the cutting edge is submitted. And here you see that when it's only a limited time, you can expose diamond PCD to higher temperatures in contact with a material in which there is iron. But when you have longer cuts, you have to be very careful. And that is what is indicated here with the blue line, the working zone. You have to make sure, depending a little bit on your time in cut, that the temperatures do not go up too high, especially when you have iron in a workpiece material that could interact with diamond, with the carbon there. Another thing you have to be aware of is that cobalt has an expansion rate which is around 4 times higher of that of diamond. That means that if you have too much heat into the structure, the cobalt is going to expand and create cracks in the structure. And where in such a way cobalt in the beginning was an advantage, it was cementing the grains together. Now it will act on the contrary. It will push the grains apart. It will create cracks in the structure. And I'm going to come back in a minute to that, because that is something we have to be aware of. In which materials do we use PCD? But I would say roughly everywhere, except materials in which the basic alloying element is iron. With other words, steels and cast irons. But for the rest, everything can be cut with PCD. Very typical PCD, we use it for non-ferrous machining applications. Aluminium is the most typical example where we can use it compared to traditional cemented carbide with cutting conditions which are 5 times, 10 times higher cutting speeds then. It offers you productivity, it offers you cost efficiency, reliability, and all that type of things. And that is and if you consider to use PCD materials, and that's why I said this should be a management selection first, because at first sight it's extremely expensive. Purchasing cost is high. Very often inserts have only one or a limited number of cutting edges per insert compared to a lot of cutting edges on a comparable thing with carbide. There's only a limited amount of geometries available, because basically we don't really need the geometries here. Cutting edges are quite brittle, and if you hear me summing it up, lining it up here, it's my God, what are we doing with PCD? But on the other hand, if you make your calculations right, you find out if you use PCD effectively, it's very often the cheapest material, cutting material there is available today. You have to be careful with catastrophic failure. Catastrophic failure due to fracture breakage, very often observed as nose breakage, and this is a mechanical thing, but it can also be catastrophic failure due to thermal wear. You remember the cobalt, and if it's exposed to too much heat, it will expand a lot more than the PCD grains will. And then it will create cracks in the structure, and that will lead in the end also to catastrophic failure. These are the two things you have to be careful with. Basically, it goes back to keeping your eyes on the temperature and time in cut. That is the thing you must keep under control. If you have that under control, the other wear patterns are following more the traditional things we already talked about in previous sessions. Summary conclusions. Carbide, the basic of today, the classic of today, it offers easy producibility. Today we can use it in a circular manner. It's not a throwaway system anymore. It's versatile, flexible, reliable. Diamond. Only good news about diamond. Diamond whatever you look at, it's very advantageous as a cutting material. There is a limit, and the limit is the combination of workpiece material, think on the iron, and the temperature and the timing cut. If that is not a limiting factor, then, as I sometimes say, diamonds are machinist's best friend. But be careful when you machine steel. It is possible, but it takes special precautions. Making a selection, I would say use tools which are available today, because if you have to do it manual, as I tried to show you here on the diagram to the left, come on, how can you use this diagram to the left to select the cutting material if you see that things are so closely together? Use modern approaches, software like Seco suggests we have, or competitors of Seco have their systems for helping you use that, and make sure you fully understand things. And in that respect, I would like to draw your attention on 3 technical guides we have available. A technical guide on PCD, a technical guide on PCBN and a technical guide on ceramics. These are available for you, of course. Again, if you want them, just send us a mail, send us a message, let us know, and we make sure you receive your own copy. Which brings me to an important session, an important part in this session, question and answer. And here I now ask, let me see if I can find the questions. Lot of questions. Other questions I asked assistance from my two colleagues to help me read these questions because after all, they know a lot more about these materials than I do. One question, that's an easy one. What mobile applications are you usually using in cutting tool calculations? But as I said, kind of every cutting tool supplier has his or her own software for it. In Seco, the software we make available for people, for our customers, we call it the Seco Selection, the Seco Suggest software. But as I said, if you say, and what about Coromant, and what about Walter, and all the others, well, they also have comparable software available. Personally, if I may add something to this, I'm waiting to see one system that covers all, but that is perhaps not for tomorrow. But anyway, a multitude of applications is available for that. Then I have a next question from Nazis. For hard part machining with more than 50 Rockwell C, do we prefer ceramics or CBN? And he makes a side remark that it's not easy to replace ceramic by CBN in terms of cost benefits. Very, very complicated question because there's a third part in the question. But let me first start with the first part. For machining materials with the hardness above 50 Rockwell C, do we prefer ceramics or CBN? And perhaps I can ask Francesc to help a bit on this question.
Yes. Hello. Yeah, this is a very good question and a very typical question in the application area for hard part turning, because the colleague asked about hard part turning. The boundary for CBN normally is 50 Rockwell C. When we think that we can start to use CBN in that case, but there are a lot of productivity requirements that can be the key to select ceramic or CBN. I believe that, as you mentioned before, Patrick, one of the most important things is the calculation of the cost of the operation. And when you have that data, you can select very well if it's better CBN or ceramic. Of course, when we talk about 55, 60 Rockwell C, CBN is always better, for sure, for hard part turning.
Thank you, Francesc. You already answered the second part also. And the last part in this question, can you elaborate a little bit on that? What variables, what parameters do you need to know, do you take into consideration if you make a selection between ceramics or CBN?
Perola, would you like to answer that question since your experience? Well, we have sound.
So can you repeat the question once again?
There are some sound problems. No problem. I will try to answer that question. Yeah, don't worry, Peo, because there are some sound problems. Yeah, the parameters, it depends of the cutting speed. This is one of the most important parameters. Second parameter is the number of pieces that you need to produce, the series. And the most important one is the tool life. Depending on a lot of factors that can influence, like the setup, the clamping, the configuration of the part, Also, it's very important to know that some kind of grades of CBN are more resistant to interrupted cuts than ceramics, for example. It's something that you need to consider when it's time to select ceramic or CBN. At 50 Rock will say, this is what we talk. When we go 55 up, you need to start to think in CBN for sure. 55.
Thank you for helping here, because if you allow me to give some comment on what Francesc was saying, because he was very correctly mentioning, in the end, we all talk about technical stuff, but in the end, it's about calculating from an economical perspective what it means to use a certain tool or cutting material, because that's the final decision ground. It starts with the tool selection, cutting material selection. I said it's a management task. They have to make the initial choice. What do I want? In then comes the technical people that have to fill in all the technical details. And based on all those technical details, in the end, and then it goes back to management, we have a ranking of this material costs less than this material when you use it for the applications we have. And that for me, I think personally, and I have a feeling Francesc said a bit the same thing here, it's that's the final decision.
Yes.
Oh, Francesc or Perola, I have this is a tough one. Which tool would you prefer to machine bimetallic material? Aluminium, silicon alloy silicon alloy A356, and grey cast iron A48.
Perola, maybe now you have the sound.
Yeah, hopefully you can hear me now. Is it okay?
Yes.
Yeah.
Now it's okay.
I would say for the grey cast iron, it's depending about the quality of the casting, I will say. If the casting are in a good level and it's free from ferrite and silicon content are okay, etc., then I for sure it's very good to machine it with PCBN. And you will have, I would say, cutting data and tool life that are incredible compared with carbide. If the material is not in the right, if the ferrite content, etc., is not in the right level, then you will have, I would say, a very, very short tool life. When it comes to the bimetal material, I will say that the PCD is the best cutting material to use. And in many of these type of materials, depending about, but it's also, I would say, you often need very sharp cutting edges. So I do actually prefer to use a PCD grade with small grain size to have a really, really sharp cutting edge. I hope that was the answer on the question.
And while you are on it, Perolo, can you elaborate a little bit? This is a very open question, and please, I should remind you that we are coming very close to the end of this session, so perhaps a very limited answer. Inconel comes in a lot of variations. Leandro is asking here. How would you say, if I say Inconel and advanced cutting materials, what do you answer then, Per-Olof?
I will say Inconel, it's also depending on what type of application.
Some problems.
I think.
Sorry?
There are sound problems.
Francesc, can you take over, please?
Yes, no problem. Yeah, you know that the three main materials to machine Inconel This is a very good question from Leandro. It's for roughing, carbide. For semi-finishing, we can say ceramics. And for finishing, here is the big discussion, can be CVN. But CVN sometimes can affect the structural composition of the material, that it's not allowed in this kind of components. For that, sometimes it's also used carbide for finishing. These variations that you mentioned, nowadays we are facing that is changing that rule that I have. And we need to take case by case to see what is the best solution that we can offer. I hope that I have answered the question. What do you think, Patrick?
Yes, absolutely. And yeah, I see the questions continue to come in, but on the other hand, we have to respect also the time a little bit. What I propose here is, if you have questions, please continue to put them into the comments. Francesc, Per-Olof, and myself, we will take care of the questions that come in, that you have an answer to all your questions. But again, as I said, we have to respect the time a little bit also here. I also bring back in mind the things which are available for you. Just leave us a message, leave us your email or something, and we if you are interested in the technical guides, we send the 3 technical guides to you. They come under the form of a PDF file. The presentation itself is available under the form of a PDF file. Also, that one, if you want to receive it, leave me a message. So if you want extra information, if you have extra questions, what I'm trying to say here is we have to close the session here. I want to respect the time, but on the other hand, let's that not stop the discussions and the questions ongoing. Let's stay in contact, and we try to help you as much as possible. The next one is October 24th, where we are going to talk about the second part when we talk about advanced cutting materials. And the second part is we are going to spend quite some time on PCBN, polycrystalline cubical boron nitride, and ceramics as the 2 families of cutting materials that makes, together with PCD, the full family complete. I would like to thank all of you who participated as a viewer, as a listener to this presentation. I hope you found some rewarding information in it. I hope we made some things clearer for you, because the selection of a cutting material, on the one hand, it is very important. On the other hand, it's not easy. There are so many different cutting materials from so many different suppliers, and if you listen to all the marketing messages, every single one of them is the very best on the world. But the machinists in the end need to make a selection, and it's not easy, and it demands serious thinking, and I would say creativity, in a sense of any cutting material is only as good as the one using it. If you as a machinist, you know what you are doing, you can make any cutting material work, by means of speaking. That's the value, that's the importance of knowledge and insight. I also like to thank my 4 colleagues, Alesia, Margarita, for making this possible. It was quite a challenge. It's the first time we had 3 people in a session, and it worked rather well, I have to say. And I would like to thank my 2 colleagues, Francesc and Per-Olof, also for sharing the expertise they have when it comes to this type of materials. And I hope all 4 of you that also the next session, you all will be there together with me then. Thank you, everybody, and looking forward to see you 24th of October.